In this section, I will introduce you to the notion of motor representation and some key discoveries about it. You may well be feeling by the end of it, well, what does this have to do with the problem of action or any kind of philosophical issues? Don't worry about that, we're going to get to those later. In this section, I just want to cover the notion itself and some evidence about it. If you've never come across this before, it might be quite difficult. So start with a simple illustration. Here's an egg. You're a chef. You reach for the egg. I'll put it down here actually so that I can reach for it and demonstrate. You reach for the egg and you move it across the room, right? Or maybe you reach for the egg a different way and you take it up. Now what's interesting about grasping the egg here is that exactly how firmly you grasp it depends on what you're about to do with it. If I'm going to move it horizontally to the side, I will grasp it in a fairly delicate way here so that I minimize the chance of breaking it while being sufficiently secure for that horizontal movement. But when I seize the egg and thrust it upwards, I'm spontaneously holding it much more firmly. Greater risk of cracking the egg, but I need the firmer grip in order to move it upwards. This is actually my last egg. You've got no idea how many times I've been doing this, so let's hope it works. It's already a bit damaged actually. Hope it works this time. Anyway, here's the thing. When I'm grasping the egg, I'm performing a very small scale motor action, and how I perform that action depends on things that are going to happen in the future. For example, whether I'm going to lift the egg up vertically rapidly or move it across slowly, smoothly. Furthermore, you will also be able to detect in how I grasp the egg something about the future obstacles that I might encounter. So if there's a hot pan instead of a handy bowl right by the egg, you might well see me approaching it with a different hand or from a different angle. Now none of this is a matter of intention or belief or desire. None of it is something that you would be ordinarily aware of, but the way in which you grasp the egg is in some sense sensitive to the things that you in future will do with it. It's sensitive to facts about the future that you determine. This tells us something very important. As Cohen and Rosenbaum say, a given motor act may change, how firmly you grasp the egg for example, as a function of what motor act will follow it. Will you lift it vertically up or smoothly horizontally? This, Cohen and Rosenbaum say, is a sign of planning. But of course you can't have planning in that sense without representation. That's why we need to postulate motor representation, or one reason why we need to postulate it. You can't have actions being sensitive to future facts that you yourself determine unless those future facts are somehow represented, unless those future facts are somehow influencing the present. Excellent. Now the question is, given that we've got a good reason to postulate motor representations as the representations involved in controlling very small scale actions like grasping an egg or moving it sideways or breaking it into the bowl, now that we've got good reason to postulate these motor representations, we need to ask the question, what do they represent? An initially tempting idea is that motor representations might represent just joint displacements, so for example the movement of this finger joint from here, and bodily configurations. That would give us a maximally simple view of what motor representations are and what they represent. And philosophers who think about this at all do indeed assume that insofar as it's not merely mindless physiology, if anything's represented at all, it will be something like bodily configurations and joint displacements, and those only. But we actually have an excellent reason for thinking that motor representations represent much richer kinds of outcome, such as the grasping of the egg and even the eating of the egg or the breaking of the egg on the vase, outcomes which are specified independently of particular bodily kinematics. And if that's true, motor representation will turn out to be much more interesting for us than it would be if we just had joint displacements and bodily features. So let's think about this carefully. How is this idea going to work out for us? Very simple thought. What's represented motorically as some kind of goal, the movement of the egg from one place to another. so on. On the way to computing how the joint displacements and bodily configurations should unfold, one needs to think about things like the starting state, where the egg is, where the hand is, where the end state is, and one needs to optimize for factors like smoothness, right? So you don't want a very jerky movement if you can avoid it. A lot of human action is incredibly, sublimely smooth. That's thanks, of course, to these motor processes. So the basic picture we've got is that the outcome that we're aiming for example, the movement of the egg is represented motorically. That triggers a bunch of computations concerning starting state, end state, smoothness and the rest, ultimately resulting in a pattern of joint displacements and bodily configurations. But of course the picture is much more complicated than that, for typically the particular action, for example the moving of the egg, occurs in a more complicated sequence, which might involve, for example, I haven't got the egg anymore, but passing it from one hand to the other and so on, in which case there will have to be coordination across many different motor acts. All of this provided by motor processes. So there's good reason to think that outcomes must be represented motorically, given what we know about the role of motor processes in planning. You can't do the coordination of the grasping with one hand and the grasping of the other hand without representing the outcomes motorically. But it would be nice if we had some more direct evidence, perhaps, that outcomes are represented motorically. So this is a good question. How do we know that those outcomes are represented motorically? In order to answer that question, it's helpful to introduce a little bit of background on something that I call the double life of motor representation. This isn't really our focus, but we'll rely on the fact that motor representations lead a double life in order to gather the evidence for the thing that we are interested in, the claim that they represent outcomes. So very quick beginning about the brain. I know very, very little about the brain. This is virtually all I know about the brain. The motor areas are towards the end of the rear of the frontal lobe, I should say, the rear of the frontal lobe. The motor areas are towards the rear of the frontal lobe. Those of you who are doing EPP, for which of course this module is core, you'll be well ahead of me on how the brain works, I'm sure. The motor areas that we're interested in are the rear of the frontal lobe, and we're talking about motor in a very broad sense to include SMA and the rest, not just the narrowly defined motor cortex. Okay, very good. Now, suppose that we have the brain, that was a human brain, but suppose that we have a brain of a monkey, which also has an analogous motor area. And suppose that we use a single cell recording technique in order to work out how a particular cell in the motor cortex fires. So what you're seeing here is time. This is roughly a second of time going on here, and you're seeing the firing rate during each of these intervals. What you can see here is that there is a monkey, and the monkey is doing something. It is grasping an object in order to eat it, and at the point at which the object is firmly grasped, you get a noticeable peak in the firing of this particular cell. Now, interestingly, this cell in the monkey's motor cortex discriminates between grasping an object to eat it and grasping an object to place it. So when the monkey is grasping the object to place it, you see a different pattern of firing, much less firing when that's happening. Very interesting. So that's already pushing us in the direction that the motor representation is unlikely, insofar as it's linked to motor neurons, to be just a representation of some kind of kinematics, right? Because we wouldn't have that discrimination otherwise. But that's a weak point. Here's the more interesting point. Take the same monkey and get it to, instead of performing the action, observe another performing the action. So now the monkey isn't acting themselves, they're observing another monkey grasping something in order to eat it. And what you see is that there's a nice peak in the same neurons firing. When the monkey is observing another grasping in order to place an object, you don't get that peak of firing. So that's really interesting. If we compare grasp to eat with grasp to place, we see that the neuron selectively fires for grasp to place. If we compare self with other, we see that the neuron is agent neutral. It fires both when the monkey itself is performing the action and when another is performing an action. This is the double life of motor representation. Motor representation is something that you see both when performing an action and when observing an action performed by another. And here are some graphs from Fagassi and colleagues' study showing just the same thing, but in a kind of summary format, right? So you're seeing here that the firing in the place to eat, summed over a variety of cases, is much higher than the corresponding firing in the place to grasp, and that you get the same peak for the other as for the self. So this is the double life of motor representations. Whether a motor representation occurs in you depends on the kind of action you're performing, but it doesn't depend on whether it's you performing the action or somebody else performing the action as well. There's a second way of illustrating or evidencing this same finding in humans, which involves the fact that motor areas for the control of the lips and for the tongue are spatially separated. This allows us to use a technique called transcranial magnetic stimulation, TMS, to selectively enhance activity either in the lip-related area or the tongue-related area. What Alcelo and colleagues did, therefore, was to present their subjects with either a phoneme like b or p, which involves the use of the lips, b or p. I think that's label, or is it dental? I'm not sure. B or p. Or a phoneme like d or t, which involves use of the tongue. If you pronounce those phonemes yourself, d, t, you'll feel your tongue in a way that doesn't. You'll feel your tongue being involved in a way it's not involved when you're p and b-ing. What they found was very simple. If you give somebody the tongue-related TMS, they will be faster to recognise the tongue-related phonetic gestures t, t, d, and slower to recognise the lip-related phonetic gestures b, p. Whereas if you give them an artificial boost via TMS in the lip-related motor area, you'll get the opposite pattern. They'll be slower to recognise the phonetic gestures involving the tongue and faster involving the lips. So here you have this beautiful interaction between the kind of phoneme that's being recognised and the part of the motor cortex that's being artificially boosted by the TMS. What this tells us is that the motor representations involved in producing those phonetic gestures are also facilitating recognition of those gestures as well in this case. And that is the double life of motor representation. The motor representations involved in providing the complex articulation of the lips, tongue, larynx and velum, which enables you to pronounce these phonemes. Those motor representations are also involved in the process of recognizing from the acoustic signal the production of those phonemes in another. Very good. So hopefully you're now clear on some of the evidence that tells us that motor representations play a double life. But all of that is important to us on this course only because it helps us to understand how we know that outcomes are represented motorically. Let me explain. What we're going to do is to look at some cases where we change the kinematics and hold the goal constant, and what we'll see is that we get the same motor representation. Then we will do the converse. We will vary the kinematics and keep the goal constant and show that we get the same motor representation. This will provide us with a good reason to think that motor representations carry information not about kinematics, but about outcomes to which actions are directed, such as the grasping of an object. The double life of motor representation is important because we're going to use paradigms in which you observe rather than perform actions to get hold of this evidence. Very good. So here's the first idea. Villager and colleagues did something very simple. They showed subjects a video of a hand grasping an egg, and they used an artificial way of enhancing the brain, the transcranial magnetic stimulation, to produce, they hoped, motor evoked potentials on the muscles in the hand of the observer, which they would be using if they themselves were performing this action. Right. So their idea was this: because we think motor representations lead a double life, when you observe somebody reaching for and grasping an egg, it's likely that the motor representations which would occur if you were performing the action will also occur in you, even though you're merely observing the action. Therefore, if we boost activity in your motor cortex using transcranial magnetic stimulation, although we don't expect we can do that enough to make your hand actually move, we might be able to register subtle electronic signals on the muscles that would be involved in the hand movement, so a kind of covert movement initiation, that are linked in time to the performance of the action you're observing. But further, this is the interesting part for our purposes, what they predicted is that we would get that in a situation where the outcome was actually possible. The hand is actually reaching for the egg and the egg is there, but they would not get that when they showed the same videos which had been edited in order to remove the target. So in this case, we've kept the kinematics constant, but there's no coherent outcome to which the action is directed. There is no egg. To be even careful, they did a second study in which instead of keeping the egg visible, they actually hid the egg or non-egg after it was there. So what you can see here in this second, more rigorous study is that the difference between the two videos was only apparent in this very early stage. After that, the two videos were exactly the same. And what you can see from the graph here is that we do actually get significantly more motor evoked potential muscle activation in the case where the object is absent than the case where the object is present during all phases, during the transport and grasp phase of the experiment, not during the reach phase. And that's exactly what you want, right? Because that's getting the activation locked to the timing. And the same thing with the other experiment. Interesting fact about these experiments, if you're an expert, is that very often when you're observing a action directed to a goal, the goal actually occurs. You usually get stronger motor evoked potentials. Here we get the reverse pattern. We actually get weaker motor evoked potentials in the actual goal case than in the disappearing egg case. But what matters for our purposes is just that there is a difference here. It's just that there is a difference here. So we keep the same kinematics, but vary the outcome, and that alters the extent to which the outcome is represented motorically. What that's suggesting to us is that the motor representation looks to be linked in some way to the outcome rather than directly to the kinematics. So what we've done here is kept the kinematics constant and varied the goal. Now what we want are experiments which do the converse, which change the kinematics but keep the goal the same. So one rather beautiful experiment by Umilata and colleagues involved comparison between reverse pliers and normal pliers and reverse pliers as tools to grasp. So when you're using the normal pliers, you squeeze them in order to grasp an object. Right? So what the monkeys are doing in this experiment is using these pliers to grasp a particular thing and then probably get to eat it as a reward. Alternatively, they're using the reverse pliers, and with the reverse pliers you've actually got to release the pliers in order to grasp. So what we've got here is the same goal in two cases, grasping an object, but in one case that requires squeezing and in the other case it requires releasing. So we've got quite a radical change to the kinematics which are involved between the two cases. And what Umilata and colleagues demonstrated, I won't show you the graphs, is that they got comparable motor representation of action across the two cases, despite the radical change in kinematics. A related study has also been done in humans by Cattaneo et al. So they were interested in speed of recognition, and so they gave people a video involving grasping an object either with the hand or with the foot, and then they were shown some test pictures which could either involve the same effector, so both times, a different effector, so either a hand or a foot, so we can vary the effector, and also could involve a different goal, so pushing an object instead of grasping it, for example. And their hypothesis was that when you keep the goal constant, it won't matter that you change the effector. Subjects will be just as fast or slow to identify the object. But when you change the goal, even if you keep the effector the same, so foot versus foot here, you will get a big difference. That will make a difference. And using a very clever TMS study, that is exactly what they found. The motor representations of action that allow people to recognize a goal appear to be linked specifically to the goal and do not seem to care about the effector. And that's interesting for our purposes because, of course, grasping with a foot versus grasping with a hand is kinematically very different. So we've got quite different kinematics, but the same motor representation. So let me give you in summary what we've looked at so far in terms of the evidence. The question is, why do we think that what is represented motorically is not merely joint displacements and bodily configurations, but rather outcomes such as the grasping of an object or the moving of an object from one place to another, outcomes which involve actions, outcomes that we could call goals. Well, the first part is that those markers of motor representation are unaffected by variations in kinematic features which don't change the goals. Right? That's what Cattaneo et al. Study shows. That's what the Umilata et al. Reverse pliers study shows. Also, they're affected by variations in goals where you keep the kinematic features constant. So those two converse findings tell us that the motor representations do carry information about goals. Now here's the tricky bit. It's one thing to say that representation carries some information. It's another thing to say that it represents something. Now I follow Dretske here in thinking that where a representation not only carries some information, but that the function it performs depends on it carrying that information, we can say that the representation represents that information. So I'm following Dretske here, and because I'm doing that, what I need to show finally is that information about outcomes is involved in the function that motor representations perform. Their function is to guide planning-like processes, and this is what we saw earlier. So imagine, for example, that you are I'm sure you've never done this, but imagine, just for the sake of argument, that you're trying to steal an apple from a grocer's stall. So you've got three tasks. You need to secure the apple, you need to transport it, and then you need to position it in your pocket. So you've got to sort of do this while nobody's looking, and so somehow transport it into your pocket, drop it there smoothly. No one will notice. Well done. Okay, very good. Now, of course, each of those actions breaks down into much smaller components. So securing the apple involves, first of all, reaching, then grasping the apple, moving, and so on. Furthermore, how you perform any of those components, for example, the grasp that you make to secure it, will affect how you transport it. If you hold it by the stalk, transporting it is going to involve very different actions from if you have a secure whole hand grasp on the main body of the apple itself. Likewise, if you grasp it from above, you're going to have a different action compared to if you grasp it from the side. So what's interesting here is that there are oh, sorry, that's the wrong button. I can't do this again because I'm on my last egg. What's interesting here is that there are relational constraints on the constituents of actions. The actions that are components of the securing phase determine what's going to happen in the transport phase. And if you've already fixed on that transport phase, then you need to modify things here. And in fact, what we know is that human action performance does indeed involve relational constraints going both present to future, but also future to present. What that tells us then is that information about outcomes represented motorically exists partly in order to guide those planning-like processes. That information does indeed serve a function with respect to motor representations. And that's enough for us to say, as I did at the start, that some motor representations represent outcomes such as the grasping of an object or the placing it, outcomes that we might think of as goals to which actions are directed.